Good morning. I'm Antonio Longa, and I'm here to present Egocentric Temporal Motifs Miner, in short, ETMM. And I'm okay. Let's start with the table of contents. So we're gonna see network motifs, egocentric temporal neighborhood, egocentric temporal motifs, the results that we obtained in the paper, and how to use the code, and finally some conclusion. So let's start saying that motifs are simple building blocks of complex networks. And in particular, we can define network motifs as a recurrent and statistically significant subgraph of a graph. So, for instance, in this image, you can see the 5 types of standard motifs. Later, researchers extended the notion of network motifs to temporal motifs. So, for instance, you can see the image at the image B, in which you can see these three nodes, three edge with an ordering among these edges. And in this work, I'm gonna present egocentric temporal motifs. So let's start and to see the model. So given a temporal graph as the one you can see in the panel, we can represent the temporal graph as an ordered sequence of static graphs. So suppose that you are gonna aggregate uh, aggregate graphs, aggregate during the time. So, for instance, in this example, from the temporal graph, you go to three different time steps. So the 0, the 1, the 2, the third. So 4 time steps. And in this little figure, I'm showing only 3 time steps. Then we choose an ego node and k equal to the number of temporal layers minus 1. And let me say that, for instance, we can choose E as a ego node, and then we build this structure. I think it's easiest to see in the temporal snapshot arrays. So suppose you are starting from E as an ego node, then you build this egocentric neighborhood. So what is simply the neighborhood, the first order neighborhood of the node, and you connect these to a second layer, a third layer, obtaining an egocentric temporal neighborhood. Yeah, for instance, in this image, you can see that the ego at the first time step, at the time 0, the time 1, and the time 3, and the time 2 is the same. Of course, the ego is remain the same. And what happened in the first in the time step 0, it is connected with A, B, and C. And in the first time step, it is connected to B and C. So since B and C are the same node in the previous layer, they are also connected with this brown line, let me say. And in this way, we have this 3D structure representing what is going on in a single static graphs, and it's concatenated with different layers, and we obtain this new type of structure. um, Let me say that the strong of our method rely on the fact that we can compute egocentric temporal neighborhood signatures. What does it mean? We have such a we are able to write this 3D structure as a graph, as a string. Okay, for instance, you can see in the panel, in the left panel, let me say, that we compute first, we compute a node embedding and node encoding, and then concatenating this node encoding, we can compute the egocentric temporal neighborhood signature. So how can we compute the node encoding? So let me say that the encoding for each node, non-ego node, has a length of k plus 1 first. And what is a big vector saying if the given node is connected to the ego at that time step. So let's start, for instance, in this egocentric temporal motifs, egocentric temporal neighborhood, we have that node A is connected to the ego node at time step 0, and then at time step 1 and 2 is not connected to the ego. So what does it mean? It means that its encoding will be 1 because at the time step 0 is connected, and 0 0 because is not connected. Let's take another example, like for instance, the node C is connected to the node to the ego node at time step 1, I mean time step 0 and 1, and then it's not connected. So the node encoding would be 1 1 0. Okay, and then when we have this node encoding, we sort the node encoding. So for instance, our 100 111 110 and 011 will be sorted in 011 100 110 111. Okay, since it's sorted, we have now our egocentric temporal neighborhood signature, and I think it's really interesting how we can convert this graph structure in a string. Okay, let me talk a little bit about the properties of this egocentric temporal neighborhood. And so given two egocentric temporal neighborhood, the associated egocentric temporal neighborhood signature are identical if and only if they are isomorphic. What does it mean? It means that with this node encoding, this substructure encoding, we are able to compute isomorphism test just comparing strings, and we have proved this. This statement in the paper. So if you're interested, go and read it. But basically, what I'm saying is that we would have the same egocentric temporal neighborhood signature if and only if we are talking about isomorphic graphs. So, for instance, in this figure, okay, I drawn the first, this first egocentric temporal neighborhood, and then I draw another egocentric temporal neighborhood, but they are isomorphic. So I just added the different labels, but doesn't really care in this example. I just want to show you that we can retrieve this. We can test isomorphism in a really fast manner, just computing the equivalence of strings. Another important property is that since we have not to compute the isomorphism test, we can build we can build a much bigger structure. Like egocentric temporal motif will be really huge in length or in number of nodes, and we can really explore several sizes in both the temporal and the neighborhood dimension. And that's all. So let's talk about egocentric temporal motifs instead. So ATM. So okay, given a temporal graph G and an n null models, we consider egocentric temporal motifs those egocentric temporal neighborhood that pass a statistical test. Okay, so first of all, let me say that we have a null model, so that we can, I mean, multiple null models, so that we can test the statistical significance of our input graph. And we then since we have what we do, we count the number of neighborhood on the null models and on the original graph, and we apply these three tests. The first one is overrepresentation. What does it mean? It means that the probability that the number of occurrence of a single, I mean, of a single motif, of a single egocentric temporal neighborhood is greater than the number of the same motifs in the original graph is smaller than a given alpha, then what we have, the minimum deviation. What does it mean? The difference about among the frequency of motifs, I mean, a neighborhood, an egocentric temporal, an ATN, minus the frequency of the ATN in the null models is greater than beta multiplied by the number of the motifs in the generated graph. I mean, in the null models. And finally, the frequency of the motifs must be greater or equal of a given gamma. Okay. So, and that's all. Let's talk about the results. First of all, I think we have this interpretability because just as a sequence of example, I'm showing the result obtained, the motifs of the temporal motifs obtained with a standard temporal motifs miner. And in the plot you can see the frequency, I mean the obtained graph in of one data set. In this case is DTU, the Copenhagen students traced with, I mean, using their Bluetooth, and this is the type of the network. As you can see, the standard motifs identifies this I mean, open triangle with ordered edges. So what does it mean? For instance, in the first image, you can see individual that talks with another individual, and then a second individual talks for for two consecutive times with the same individuals. And we think that with our method, you can build really more understandable motifs. What does it mean? For instance, I'm showing the 5 most frequent motifs. So the first motifs is, let me say, it's obvious. What does it mean? It means that the user, the ego node talks with a person, and the conversation belongs, as a length equal to the motives. And then we have that a person talk with 2 guys, then with 3 guys, and then we have this fourth motive that a person talk with a guy for a length, a long period, and then another guy join the conversation. Or another example is, another motive is that 2 guys start a conversation, and one left, and another guy keep talking with this the first guy. And we think that our egocentric temporal motifs are easily explainable and with respect standard motifs, especially in the context of face-to-face interaction. In the second part, we show the effectiveness of egocentric temporal motifs mining in terms of distances. So let me just say that we define this egocentric temporal neighborhood based distance that basically is the cosine similarity about two embeddings. Okay, so let's see in detail how it's defined. Given a set of motifs, so M, the distance based on M of G1 and G2, that are shoe graphs, is 1 minus the embedding on base M of G1 multiplied by the embedding on the same base, so M of G2, divided by the norm of the embeddings, the product of the norm of the embeddings. Okay, we have to say what this embedding is. So the embedding on base M of G is an embedding, of course, of G in a vector of cardinality length of M, okay, in which the ith element of the embedding represent the number of the occurrences of the MI motifs, MI motifs in the graph. So basically, what does it mean? It means that we have an embedding, and in this embedding, we represent in each position the frequency of motifs. Okay, so we have this sorted number of motifs, and then we count how many times these motifs appear, and the embedding will be the frequency of that motifs on the graph. Okay, and we can compute this for different graphs, obtaining this, and then on the base of this we can define this distance. What we show that this distance is really effectiveness on social content data set. We in the paper we tested this with like 5 competitors, I think, or 4 competitors, and we show the result and we compare with our result. In this talk, I'm gonna show you only our results. First, in the first table, you can see distances among different social contexts. So we have these data sets in which we have interaction among people, and we have a workplace, an hospital, 3 different high school, then we have a primary school, and a university. DTU blue is a university. Okay, let's go in detail. So all of this data set contains face-to-face interaction, and this data set has been collected by social pattern, and you can find the link on the citation here. On the bottom of the slide. And then you have the DTU Bluetooth, that is a collection of interaction data, interaction among people, among university students, in which they are using the Bluetooth and not this social pattern badge that they use. But okay, we have said something about the data and what's the new. So if you have a look on the distances based on the egocentric temporal motifs, you can easily see that there is a huge correlation among similar social contexts. So let's start with the obvious one. The 3 high schools are really closer together. So the distances among high schools is really close. They are really close in this embedding. Okay, it's the same for the working places, both the workplace and the hospital. As you can see, the distance among them is 0.07. We have the primary school, so this PS and primary school, that is the only one that is really different among each other. So as you can see, there is, for each of those networks, it's different, and also for with the university is different. Then what we have the DTU, so these university students, and interestingly, they are quite similar to the high school students, but in some sense they are also similar to workplaces. Okay, makes sense. And so in this plot, this table, I'm showing that we can use egocentric temporal motifs to compute distances among social contexts. In the second table, I'm showing distances among call, SMS, and email networks. And again, as you can see, we are minimizing, in some sense, the distances within the same group. So SMS networks are closer to themselves, email network as closer to themselves, and it's the same for the calls networks. And this is our how we showed, how we demonstrate the effectiveness of our algorithm. Practical part, you can find all the code on GitHub. You can also find a simple blog in which I talk about how to use it. And now we can move to the Jupyter Notebook to show you how to use this code. Okay. So first of all, let me say that you, as I said, if you download the repository, you can clone it, and you will have a short introduction on how to use it. And then you will have two Jupyter notebooks, example, Egocentric Temporal Motifs Miner, and example graph distances here. And we are going to show, in this short talk, we are going to present them. So let's start with with example Egocentric Temporal Motif Miner. First of all, you have to import the construction, the Egocentric Temporal Neighborhood, and the Egocentric Temporal Motifs Miner modules. When you have imported, you can, so far, you have to specify the number of K, the temporal gap in which you would like to aggregate, if the dataset will be labeled, in this case, let our false, and the file name. Then you load this data, and let's have a look at the data. So if you have a look at the data, you will find that it's simply an array in which we have the temporal time step, node A and node B. Okay, starting with this data, we build the graph. In fact, if we go inside graphs, you can see that we obtained with this gs dot build graphs data gap and no label, with label false. We obtain this array of graphs, and in particular, they are network X graphs. You can do whatever you want, like edges. We know this from network X. You can see the edges of the particular time step of the graph. And okay, this one is just the construction. Since when you have loaded the graphs, you can just use this function count egocentric temporal neighborhood of the graphs given k, and no metadata is given because it's not labeled in this case. And then what we do, we just sort the ETN with respect to their values, and then we store in the ETNs. Let's have a look. As you can see, it's really fast. I mean, just I think less than 1 second to run it. And we counted the egocentric temporal motifs in the graph. If we have a look to the S, I mean to this the egocentric temporal neighborhood, the egocentric, I mean the S, the count of ETNs of ETN. It's a dictionary in which we have the ETN, that is a binary. I mean, it's a binary string in which we have this. Here is the ETN, and this one, and so on and so forth. Okay, and then we have the count, how many times they appear. Okay, cool. We also use this function to store in this folder the data. Okay, what we have to do next, we can, of course, we can load. So we store it, we reload them. So, but it's just, then what we can do, we can draw it. It's quite easy. We have this from egocentric temporal neighborhood string to egocentric temporal neighborhood. What does this function do? Basically, this function compute start from a string, the ETNS, and it builds a network graph, a network X graph. And we also have this draw ETN that basically draw the egocentric temporal neighborhood with the red ego node and blue other node with a smaller size. And here we can plot, I mean, it's just some example. So we can plot the motifs 100, obtaining this. What this means, the person interact with a guy, then another guy, and then a third guy, and the conversation persists for several times. And we can take whatever motifs we want, and it's here. Okay, we have this simple function that plots multiple ETNs, but it's not really interesting, let me say, with their counts. So the most frequent basically is the simple one, and then we have these other figures. Okay, so let's start about the motifs. First, we build a null model. To build a null model, what we do, okay, we load the data and we shuffle the temporal dimension. Why we do this? We do this because we want to lose all the temporal correlation, and we want to exploit the temporal correlation. And with this null model, we remove all the temporal correlation, and then we analyze it. Okay, but you can use any kind of null model you would like. So let's start with this toy example with 10 null models. So we generate them, okay, and we load the egocentric temporal motifs from the, I mean, we stored before. We load them, and then we use this ETN to count the ETN in the null models, and then we store this file. So I would like to show you how fast it is. We are counting every done 1, 2 is one graph, and we are counting egocentric temporal motifs in a file. So we have this temporal graph. It's a real temporal graph. I am using a workplace, the same data set we use in the paper. It's really fast because we generated 10 null models. We counted the ATN in each null model. So it's really fast, this method. And if we have a look at the counts, you can see that we have the motifs and the frequency. The frequency on the original graph is in the first place, and then the frequency on the null models. It's cool, isn't it? I mean, here you can see that we have these kind of motifs appear 500 times in the original graph, but in null models basically less than 100 times. So it may be interesting, okay? And what about this one? So, by the way, and then we have, I mean, we would like to filter those motifs to find, to filter this egocentric temporal neighborhood to get these motifs. So what we do, we define, as Milo did, Milo et al., Ron Milo did in his work in 2002. We apply this basic statistical test over representation, minimum deviation, and minimum frequency. And just it, we computed. So what happened? We have the number of ATNs were 392, and the number of motifs, so those that passed the statistical test, are 32. Let's have a look of the shape of these motifs. And so you can have the count, how many frequency these motifs appear. You have that it's a motif because it passes the statistical test. And here is the clue part of our work. And then what we have an example of graph distances. So simply, you import the construction and the distances. You can compute the distance using ATM or ATN. Okay, you have to specify the gap, the temporal gap for aggregation, and the K. You have to specify the statistical test applied in defining the number of it's used to compute the motifs. And what you do, simply you just give the number, the name of the data sets and other parameters, and you obtain that. In this case, the dataset one was the high school. We started with 392 ATN. We filter out for 53 motifs because we have a smaller gamma than the previous experiment. In the hospital dataset, that is the second one, we started with 4,367 ATNs. We compute ATM, okay? And then we compute the distances among those datasets, and we report these ATNs. And that's all. The code is already implemented. You can use it. It's obviously free. If you have any suggestion to how to improve this code, there is a issue template on the GitHub repository. So feel free to say whatever you want. In order to conclude this talk, let me say that in this work, we present a novel approach for mining temporal motifs based on the egocentric perspective. And in a few words, ATM are simpler at topological level with respect to standard temporal motifs, and this allows us to account for larger neighborhood and to explore more in detail the temporal aspect, okay? And ATM are faster than standard techniques because they do not require isomorphism test. And what we do, we show the interpretability of the method, I mean, the interpretability of ATM with respect to standard temporal motifs. And we also show the effectiveness of egocentric temporal motifs base distance in classifying on several different social contexts. And thank you everyone for your time. If you have any further information, I mean, if you require any information, if you want to talk, feel free to contact me. You can find me 3 emails, my emails. So text me. I am really available, and I really appreciate to discuss about an improvement, problems, different direction, and that's all. Thank you for your attention.